Hey, Dr. Schmidt.
Oh, Joe.
How are you?
Good. Good to see your friendly wallpaper.
I had trouble with the homework.
Oh, well, good thing we're going to go over it.
I think I wasn't the only one. Hey, Dan,
Luis,
¿cómo estás?
bien, ¿te acuerdas qué número de cuarto era? Que no me acuerdo.
¿Por qué me voy a acordar yo de tu número de cuarto?
No sé.
¿Lo necesitas saber
Sí,
para...
mandar a recoger mis cosas.
¿Cuándo vas a ir?
Yo no voy a ir, voy a mandar a mi advisor.
¿Por?
No puedo ir ahorita.
¿Le dio la opción tu advisor? Me
Sí,
dijo que sí. Ay, no manches, bro. ¿Por qué no? Mejor ve cuando vaya yo.
pero yo no hay, o sea, no voy a ir antes de que ya cierren y no lo pueda recoger. Si no vas a recogerlos a cierta fecha, va a ir tu advisor por ellos a la fuerza.
Ah, gracias, Javi. ¿Qué tal? Tus TikToks están malísimos.
Missing Quinn and Will here.
¿Ya me creció el pelo? No.
There's Quinn. Okay. Somebody want to text Will?
I'll text them.
All right. Well, we're going to get started without him. First thing we should do is go over the homework. So how about number 1 here? Did this one give anybody any trouble or you have a question? Yeah, Quinn? Oh, here comes Will. So what did you say, Quinn?
I said for mass, it's the heavy truck.
Mm-hmm.
Sorry,
And
Dr. Schmidt.
greater momentum is rolling skateboard.
Yeah, and why is that?
Because
What the heck?
because a rolling skateboard is moving, so it has more momentum.
Well, and how much momentum does the heavy truck have?
0.
0, right? Because momentum is mass times velocity.
Yeah.
Okay. What if we take number 2? What if we take the force of an impact and we do it over more time? What happens to the impulse there?
It increases.
Yeah. Why does it go up? Well,
Oh, I was raising my hand. I thought it would decrease
why?
the impulse, because isn't the impulse like the amount of like the amount of force at a given time, like pushing into it?
Two definitions of impulse, okay? The first, I'm just going to do IMP for the definition. Remember, it's abbreviated J, but that doesn't make any sense. So impulse is equal to the force.
Oh wait, no, never mind.
Multiplied by the time.
Yeah, I actually said the impulse. I forgot. The impulse
Bigger?
will go up.
Yeah.
And it'll go up. Wait, yeah.
Well, because the force the time goes up. So and you're multiplying by a bigger number.
Yeah.
So that's going to make more of an impulse.
Yeah.
Dr. Schmidt.
Yeah.
So the impulse increases.
Yep. All right. So suppose the duration of impact on an object is doubled. Okay. So again, if you look at the impulse equation.
J equals F times T.
Yep.
So impulse equals force
Multiplied by time.
Okay.
Right? So if I double the time, what's going to happen to the impulse?
It's gonna go up 50%.
Well, I'm going to double this number here.
Oh, so it'll just go up by.
Yeah. Should you ask for, assuming your boss says, I'll give you whatever raise you ask for, should you ask for a 50% raise or a double raise?
Double.
Double, yeah. Okay. So this is going to be multiplied by times 2. Now remember that impulse has two definitions. It equals force multiplied by time, and then it also equals change in momentum. And momentum is abbreviated P, because remember M makes it look like mass, so we don't do that. We use P instead. Okay, so if the impulse is doubled, how much is the momentum change increased?
Doubled.
Mm-hmm.
So the impulse is, how much is the impulse increased? It is doubled.
Yep, the impulse is the same thing as change in momentum. So if the impulse is doubled, the momentum change is doubled because they are the same thing. All right. So why is it good for a collision to take place over less time, assuming that you don't want to hurt the person? All right. We haven't heard from Lydia.
Huh?
Why is it good for you to have a car crash over more time?
Oh, because it like reduces the force impact on yourself. Yeah.
Yeah, remember the impulse is equal to the change in momentum, and that's always going to be the same. You're always going from some velocity to 0 in a car crash. And so that's always going to be the statement. You really have two choices here. You can either make that momentum change with a really tiny force, okay, and a really big time, or you can use a really big force and a small time. Of course, you can also do like a medium amount of each. Right, and it's better for you to do that with a small amount of force, assuming that you want to live. Okay, so let's see. Liz.
Wait, can you stop 1 second?
Yeah.
My OneNote deleted everything I had done.
Oh, that's gotta be really frustrating.
Yeah. So on the third one, the impulse is the same as a change in time.
Momentum.
As a change in momentum.
Yeah.
Okay, and then on 3B, how much is a resulting change in momentum increase? It is doubled.
Yep.
Okay. Or in a car crash. Why is it? Wait, can we do 4 again?
Well, as Lydia was saying, if you have a more time, that means less force. So you have to do the same thing. So you have two scenarios you're considering here. In both cases, you go from having some velocity to having no velocity. because you've come to a stop, right? And you can either do that over a quick amount of time, which takes a lot of force, or over a larger amount of time, which takes less force. Okay, and you want to think about which one of those two things, which of those two things would be better for you?
The one that takes less force.
The one that takes less force, exactly.
Okay. Okay. And 5.
Okay. So 5. So if we take the impact and make it 4 times bigger, right? So if we're looking at this equation here, okay, so remember the change in momentum has to stay the same no matter what we do. Then if we make the time, right, so that is equal to the force multiplied by the time. So if we make the time 4 times bigger, what's going to happen to the force? Okay, to get the same number. Right.
Is it going to like extend by 4 times or something?
So let's use some numbers as an example. Let's say the momentum change was 100. Okay. One way to get that would be to use 100 newtons times 1 second.
Wait, can you stop 1 second? Because I need to go get my status.
Sure.
Okay. Thank you.
Okay. So and the unit of momentum, I think I forgot to say it last class, but the unit of momentum for once, they didn't make up a new unit. It's the kilogram times meter per second. Okay. That's just what it is. And for once, physicists write out 4 letters instead of making up another unit. I don't know why.
1 second.
So one way of getting a momentum of 100 kilogram meters per second is to take 100 newtons and multiply it by 1 second.
Okay.
Okay. Now, if I take the time and instead make it 4 seconds, so I make it 4 times bigger,
Okay.
okay, what happens to the force?
It becomes 4 times. It becomes 400.
It becomes 400. So what you're saying then is 400 times 4 is equal to 100?
No.
No,
It's 25.
25. So 25 works, right? So if I take the number, if I take the time and I make it 4 times bigger, what happens to the impact, the force?
It becomes 4 times.
Not 4 times bigger,
No, 4 times lesser.
4 times, yeah, lesser or smaller.
Okay, 4 times smaller. Okay, and 6 you can divide. What's a sagging sheet?
So it's just a sheet being hung from the wall, like not against the wall, but like like
From the
a
sheet.
from the ceiling, or like from a laundry line or a clothes line, drying line. So Liz, we haven't heard from you yet today. Why can you throw an egg against a sheet as long as the sheet is just hanging from the wall, doesn't have anything behind it?
The sheet will make the amount of time for it to stop longer because it's a sheet and it goes like so there won't be as much force, so the egg won't break.
Won't it also make the collision like less hard?
Well, that's why it makes it less hard. That's what we're learning.
Oh.
Okay? It makes it less hard by making the time longer. So when the egg comes and it smashes into the wall, it immediately comes to a stop very quickly, right? And so it then crunches and goes, right?
Yeah.
But if this is then a sheet, when it hits the sheet will like fold around it and bring it to a stop slowly over time.
Yeah.
Okay. And then it will not break then, and it will come falling down and then break when it hits the floor.
Okay.
Right? Just like if you're going to catch an egg, do you keep your hands really firm? You have to like move your hand with the catch if you want to try to catch it. Have you ever done that thing? Sometimes they do this as a bonding exercise where they fill up water bottles.
No, it's water balloon toss.
Sorry, water balloons. That's what I meant to say.
They also do eggs, I think.
They do what?
They also do it with eggs, I think.
Eggs. Oh, well, that's people feel icky about eggs, but you get a little water on you and you're mostly fine, unless you're a witch or something.
Also, eggs are pretty wasteful because like those could be like eggs that you just like.
Yeah.
What's the unit for momentum again?
Kilogram times meter per second.
So it's just 16 kilogram. So number 7 is just 16 kilograms over meter per second.
Yeah. So remember, to get full credit here, you have to write out your equation.
Yeah, P equals M times V.
Yeah, exactly. Excellent. Good job. All right. So then that then change in momentum. So for B, right, that change in momentum is equal to the impulse, which is equal.
So impulse equals force times time.
Yeah.
And what's the force here? 18? No, not 16.
Well, the momentum is 16, right? And then that is equal to the force times 0.5.
So why are we, so triangle P equals X times T.
But what's the unit for momentum?
Kilogram times meter per second.
Oh, yeah.
Right, so now we can find the force.
16 divided by 0.5? No.
Yeah, that's right.
That's 8, no?
No. So 8 times 0.5 is what?
4.
4. So that doesn't seem right.
Yeah, it's 8. 16 times 0.5 is 8.
Well, 16 times 0.5 is 8, but you just said that I should take 16 and divide it by 0.5.
32.
32.
Okay. And what average force does the pillow exert on the ball? What does that mean?
Well, you said that it was 32 newtons that the ball puts onto the pillow. So how much does the pillow put onto the ball?
I don't know. Wait. So force plus 32 newtons.
So this is a bit of a review question I snuck in there from a long time ago. All right, remember what Newton's third law says?
Yeah, that something
Right.
will go up unless there is. No, that's
Now, that's the second. So, in the third law, it says that all forces are interactions between two objects.
for
Okay.
every action there is an equal and opposite reaction.
Yeah, that's what Google says. So there's always, for every force, and in two objects being involved. Okay.
Yeah.
But there's only one interaction between them. So it doesn't matter which direction you look at the interaction. It's always going to have the same value.
Wouldn't it be 8 times 0.5 instead of 16 times 0.5?
Why?
Oh wait, no, it's 16 equals F times 0.5.
So if you have an interaction between two objects, then it doesn't matter. So like if I give Lucho $100,
I would
okay,
like.
he would like that, and I would feel sad because I lost $100. But of course, I'd feel great because I helped Lucho out. But that's one interaction, but there are two people involved. Okay, forces work exactly the same way. There are two objects involved, but the amount of force stays the same. Right? So if the ball puts 32 newtons into the pillow, what does the pillow put into the ball?
If that what 32 newtons.
32 newtons, because they're the same. It's the same interaction. So both sides of it involve the same amount of force.
And then what average is it? So is it just 32 newtons?
Yeah, because of Newton's third law.
Oh, okay.
All right, so today we're going to talk about a couple other things that help us start our next thing. First of all, I'll remind you that the units of momentum are kilogram times meters per second. I just wanted to make sure that was written down in our notes. All right, and then next we're going to talk about bouncing. Okay, so let's consider a ball. Okay. So here is a basketball. All right. And the basketball is going down with a speed of 5 meters per second. Okay, and let's just say that the basketball, it's not really a basketball. Let's say that it has a mass of 2 kilograms. I don't know what ball has a mass of 2 kilograms. It's a pretty heavy ball. All right. So the ball is going down with a velocity of 5 meters per second. Its momentum is equal to its mass times its velocity, right? So the momentum is equal to 10.
Can you not do these notes in? Can you do these notes in OneNote?
Yeah, I am.
Oh,
But I will make sure that I write them in OneNote. I forgot that I wasn't doing that.
annotating.
Yeah. Thank you. Okay, so I have a nice green ball here. It's going down. Its velocity is 5 meters a second. Okay. And then its mass is 2 kilograms. All right, so the momentum of the ball is the mass of the ball times the velocity of the ball. And the thing that you should remember or learn right now is that velocity has a direction, if you remember that from before. Okay, so since velocity has a direction, momentum also has a direction. So this is 10 meters per second down. Okay. So then the ball bounces. And now the ball is going up with a velocity of 5 meters per second. And the mass is still the same. Okay. So the momentum now is still 2 times 5. And then that equals 10 kilogram meters per second. Now, you might think that that means that they're the same, right? But in actuality, they are very different from each other because this, after the bounce, the ball is now going up. So I'm going from 10 down to 10 up. So if I look at the change in momentum, because the change is quite big, right? So that means that we need to keep careful. So this means that whenever you're describing momentum, use negative sign to indicate going down, okay? Or left. And I just picked those because those are the most common things. This is somewhat a matter of personal preference, but you folks will get less confused if you just follow my advice here. Okay. So in actuality, the ball starts off with a momentum of negative 10 and then goes to positive 10. And what's the difference between negative 10 and positive 10? How big of a difference is that? In numeric 20, exactly. So then you can find the change in momentum. And change of anything is always equal to final minus initial. And the final momentum is positive 10 because it's going up. And the initial momentum was negative 10 because it's going down. So that's positive 10 minus negative 10. So the change in momentum, oh, I'm annotating again. Sorry, I do that by habit. I was wondering why it was nice and green. Okay, so the change in momentum is always final momentum minus initial momentum. And that is positive 10 minus negative 10. Or, as Lucho says very nicely, 20.
And it's always good. The change in momentum is always going to be 20, or just in this.
No, just in this example.
Okay.
Okay, the change in momentum is always the final value for the momentum minus the initial value for the momentum. And what I'm telling you here is that you should really pay attention to the direction the momentum is. And if it is down, you should make it negative. And if it's to the left, then you should really make it negative. Okay, so what this means is that, strangely enough, bouncing is that whenever something bounces, it has more change in momentum than if it just stopped. Okay, so if you take a ball and you drop it to the ground and the ball is flat and it just goes and sits on the ground, that's not as much change in momentum than if the ball bounced and came back up.
It's double, no? Like if it stays.
Yeah, so assuming in a very simple case where it bounces up with the very same amount of speed that it bounced down, which is mostly true, but real balls lose a little bit of energy. Remember how we talked about the thermal reservoir last unit and how things would heat up a little bit? So close, but not quite.
Yeah.
Okay, so that is bouncing. So if you do, say, a karate chop, okay, and you want to chop through a board, you want to hit it so hard that your hand bounces off the board, like that. Okay, because that's going to result in more force, because that's going to be a bigger momentum change, and that means a bigger impulse. If you are ever in the situation where a civilization collapses so much that you need to set up your own water wheel to make your own wheat or make your own generator, okay? They made up a better water wheel. You know what a water wheel is? It captures the stream going by it and turns a wheel, which then can do useful things for you. It's a good idea to make the water come down and bounce out of the blade. Okay. And then that makes for a bigger change in momentum. Okay. So that's bouncing. That's a really important way to get more momentum change out of a situation. So next we have the law of conservation of momentum. And that just says, as long as no outside forces act on a system, the total momentum of the system is equal to, will stay the same. So the total momentum of the system is adding up all the momentum of each object in the system. Okay, so if I have an example here, so let's say that I am taking my skateboard. Oh, there we go, annotating again. Really gotta stop doing that. All right, let's, okay, I'm gonna make my skateboard purple. Okay, so let's say that I am riding my skateboard. Okay, so here I am riding my skateboard. Okay, and this total momentum of me and the skateboard let's just say that the momentum of me is 40. And the momentum of the skateboard is lighter than me considerably, so let's say it's 5. Okay. And I am cutting off to the right here. Okay, so what would be the total momentum of the system? I'm 45, the skateboard is 5. The total momentum then would be 45.
You just add them together.
Yeah, that's what total means. Okay, so I'm not a very good skateboard person, all right? And I sort of lose my balance, okay? As we're driving along, I lose my balance and my skateboard shoots out from underneath me, okay? So there's no outside force acting on my system, at least to the right and left, okay? Technically speaking, we mean that the forces are balanced on the system. So there's no outside force. So a little while later, my skateboard shoots off to the right really, really fast. Okay. So a little while later, okay, my skateboard now has a momentum of 50 kilogram meters per second, because it's just really going fast. I shot it out. Okay, so what's going to be the total momentum?
95.
So what's the law of conservation of momentum say?
Isn't it 90?
Yeah, but what's the law say?
As long as no outside forces act on the system, the total momentum
So the total momentum of the system will stay the same. Okay, so my
45.
skateboard is shot out from underneath me. Is that going to affect the total momentum? What does the law tell us? Right?
It
No.
won't.
So I like that. No. So the total momentum is still 45. Okay? So therefore, my momentum must be what? Okay. So the skateboard's momentum is now 50. The total momentum has to stay the same. So my momentum then must be what?
The same, right?
Well, the total momentum has stayed the same. That's all the law says. The law just says that the total momentum has to stay the same.
Oh.
So the total, adding them up together, has to be 45. The skateboard is now 50. So therefore, my momentum
-5.
has to be -5. Because my momentum of -5 plus the skateboard of 50 makes 45. Okay. So therefore, this is why if you do this in real life, if you've ever done this, right, I am now going this way.
You fell off the skateboard.
Yes. Right, and this necessity that momentum has to stay the same for the total is why you fall off the skateboard. So there we go. All right, we can try some more examples. Okay.
Can we
let's,
try worksheet number 2?
What?
Can we try worksheet 2?
Worksheet 2 doesn't have too many of these. Worksheet 2 is mostly an extension of these concepts to make sure that you understand them. This is really useful. So the law of consummation in collisions. Because during a collision, there's a lot of forces involved. Okay? Things are going every which way. And the forces are not doing us the nice benefit of staying constant. They're changing a lot. But if I make my system both cars involved in the collision, or both objects involved in the collision, then all of the forces will be inside forces, inside of the system. And so there will be no outside forces acting on the system. And so the total momentum will stay the same. So if I have 2 bumper cars, okay, let's say we have a green bumper car It's very important to draw a good car. So I have a green bumper car. And let's say the green bumper car is traveling to the right, and they have a momentum of 20. Okay. Then there's a blue bumper car. Excellent. Okay, and they are driving to the left. And they're not nearly as confident. So they start driving to the left, and their momentum is -5. So then let's say they bump together. And then after the bump, let's say the green cars come to a stop. So the green car is now super dizzy. Okay, so they're now to stop. What's their momentum if they're at a stop? That's right, 0. Very good. Okay, so now I want to try to figure out what the blue car's momentum must be.
And wait, and it has to be. They have to add up to 20 or 15.
15.
The
Okay.
blue
So
cars-
yeah. What do you think, Will?
The blue car's momentum is going to be 15.
Right. Because the total momentum is 15 up at the top. So what's the total momentum at the bottom? Still 15. So therefore, right, the momentum of the blue car must be 15. Because the green car was 0. Okay. All right. Now, there's 2 kinds of collisions. Do this really quick, and then I have a fun video to show you. So 2 kinds of collisions. Just some vocab words. There's elastic collisions. So in an elastic collision, the 2 objects bounce off each other. And kinetic energy is conserved. So the total kinetic energy is conserved. All right, that turns out to be, you can do some really fancy math with that, which we're not going to do. Okay, but that's an elastic collision. So basically, an elastic collision is when things bounce. And then you have inelastic collision. In an inelastic collision, the 2 objects stick together. Right, so if you've ever done, if you've ever had those Velcro ball things, or if you have a ball, like the Velcro ball things, or you shoot where you throw the ball at the little Velcro paddle, and then you catch the ball, and the ball sticks to the Velcro paddle, and they stick together. Or if you have a train car colliding with another train car, and then they stick together because they couple together. Okay, that's called an inelastic collision. Okay, all right, so I wanted to show you one of the most famous examples of this. Okay, and that is called Newton's cradle. Right, so here it is. I'm sure you've seen this before, right?
Yeah.
Yeah, so let's watch what happens. Right, so I'm gonna back it up a little bit. Okay, so each ball has a momentum, right? So I'm gonna annotate now. So this ball has a certain momentum, okay? And then it comes and collides with all the other balls. And then the momentum has to be conserved, so that same amount of momentum has to pop out the other side. Does that make sense? Do you have a question, Will?
Yeah, does it have to be 3 balls in between, or can it be 1 or 2?
It can be any number, really. I mean, technically speaking, remember that every collision puts a little bit of energy into the thermal reservoir. So if you had like 100 balls, then it would probably not work. Okay, but that's only because of the thermal reservoir. But it can be 1, 2, 4, 27. You know?
And that's why it's not a perpetual motion.
Yes, that's why it's not a perpetual motion machine. It will stop eventually, because every collision puts some energy into the thermal reservoir. All right, so let's see what happens if we keep going and we do 2 balls. Okay, so again, now we have twice as much momentum coming in. And so that means on the other side, we need twice as much momentum coming out, because the momentum has to be conserved.
What if you did 3?
Oh, let's see what happens. That's it. Right? So with 3, you still have to have three balls worth of momentum coming out the other side. So that middle ball just keeps going.
Does it ever end?
Oh yeah, it ends pretty quickly because of that thermal reservoir thing we were talking about. It's already kind of dying down. Okay, incredible science.
If you did 4, would 1 stay there? And
Yep. Yeah, if you did 4, then 1 would stay there, and the 4 would just keep going back and forth. Right? So this is a pretty common toy. You may even have one around your house. I don't know, but they're really interesting. They're really cool demonstration of conservation of momentum. All right. So your homework is to do worksheet 2. I'll show you that really quick. Okay. So worksheet 2. When you throw a ball, do you experience an impulse? So this is back to talking more about impulse. I want to make sure that you understand what impulse is. It's force multiplied by time, and it's change in momentum. It's both of those things. So I want you to make sure and explain your answers here with at least 2 sentences. So try to make some connections between what we talked about with bouncing today and impulse. Right. Do you all know what recoil means?
Kind of.
Kind
It's
of.
like
So if I like take a gun and I shoot it, the gun will go backwards.
mhm.
Okay. That's true for any gun, especially a big gun like a cannon, which is a very big gun. The cannon will go backwards. So explain why that happens. And then there's a couple calculations. Well, one quick calculation again, and then you're riding a bicycle at full speed and the bike stops suddenly. Why do you have to hold on to the handlebars really tightly? All right, so I want you to try these. We'll go over them next class and discuss them some more. I think this stuff is pretty interesting. Hope you're enjoying this. All right. So have a great afternoon. Don't forget to vote if you're in the class of 2023, which I think many of you are. All right.
Thank you.
Thank you, Mr. Smith.
Bye, Don.
Have a good day.
Joe.